Hello, and welcome to another day in AP Stat. Today, we're going to be starting chapter 9, and in this chapter, we're going to be looking at a different type of inference test called a significance test. The first thing we did with inference is we looked at confidence intervals, which is one of the two most commonly used statistical inferences that we have. The other type of common inference is using what's called a significance test. A significance test starts with making a claim that we call a hypothesis, and we want to see if this claim is true or not. The claim is a statement about the parameter, like the population proportion or the population mean. We express the results of a significance test in terms of the probability that measures how well the data in the claim agree. Okay, we're essentially making a claim about a population, and then we're using sample data to determine if that claim is feasible or not. So we're going to start today by looking at an example. And the example is looking at the proportion of free throw shots made. Now, every single significance test starts with a carefully thought out hypothesis. We have a null hypothesis and an alternative hypothesis. The null hypothesis is a statement where there's no difference, meaning we assume that the statement is true. So, for example, let's have I claim that I can go and shoot and make 80% of my free throw shots. Okay, so I claim that I'm an 80% free throw shooter. So my null hypothesis would be that P is equal to 0.8. An alternative hypothesis is where we're trying to find evidence against the null. Okay, now an alternative hypothesis could be one-sided, it could be two-sided. So in our example that we're going to be working through, I claim that I can shoot and make 80% of my free throws, and you as a class say, no, Mr. Walsh, I think you stink at basketball. I think you shoot less than 80%. Okay, so you're always comparing it to the null hypothesis. So I have P is less than 0.8 as my alternative. And the symbols that you use are H sub 0 for the null hypothesis and H sub A for the alternative hypothesis. So these are the two hypotheses that we're going to be working with today. Now, hypotheses is the null hypothesis is always a parameter equals a value. So it'd be like P equals something or mu equals something, because our hypothesis is about a population, not a sample. Alternative hypotheses are going to be in the forms of the parameter is not equal to or an inequality, like parameter is less than or greater than a value. And these values need to be the same. Okay, so the null hypothesis value is the same value that we're comparing the alternative hypothesis value to. An alternative hypothesis could be one-sided or two-sided, like I said. A one-sided alternative is looking at just one side of the or one tail of the distribution. So in our little example, we're doing a one-sided test because you don't care if I can make more than 80% of my free throws. You only care if I can make less than 80% of my free throws because you think I stink at basketball, not because you think I'm good at basketball. A two-sided test is just looking at the difference, meaning is the parameter different than your null hypothesis? So, for example, if I said I can shoot and make 80% of my free throws, and you guys just said, no, Mr. Walsh, you can't. You didn't care if I was better or worse. That would be a two-sided hypothesis where your alternative would be a not equal symbol. Okay, so it could be one-sided or two-sided for the alternative hypothesis. The hypothesis should express the hopes or suspicions we have before we see the data, meaning it is cheating if we gather the data and then form a hypothesis based off of the data that we get. That's cheating. Number 2, the hypothesis should always refer to the population, not the sample, meaning that you're going to use either P or mu when dealing with population parameters. You're never going to use P hat or X bar when making hypotheses, because those are characteristics about a statistic or about a sample, and that we can find. We're not estimating a sample statistic, we're estimating a population parameter. All right, so suppose a basketball player, that's me, claims to be an 80% free throw shooter. To test this claim, you guys come to my house, and I have a basketball hoop outside, and I shoot 50 free throws. After shooting 50 free throws, I only make 32 of them. So even though I claim to be an 80% free throw shooter, I only make 64% of the free throws when I take a sample size of 50. What can we conclude about this data based on this sample? Well, instead of looking at a single sample of 50 shots, we're going to use a simulation. And this simulation is going to take 400 samples of size 50 of a person who really is an 80% free throw shooter. So you don't know if I'm an 80% free throw shooter. I'm just making that claim. So let's go to our simulator, and we're going to take 400 samples of size 50 of a person who really is an 80% free throw shooter. Because if a person who really shoots 80% was to take 50 free throws, they're not going to make 80% every time. Like, they're going to make 41 sometimes, they'll make 38 sometimes, they'll make 44 sometimes. They're not always going to make 40 out of 50. So here is our distribution of the 400 samples of size 50. What we created was the beginning of a sampling distribution with sample size of 50. Okay, we use a simulation to create the beginnings of a sampling distribution. So because I have 400 samples of size 50, if I was really an 80% free throw shooter, this would be approximately my distribution. And because we got a sample proportion of 0.64, you will see these are all the times I would have shot 64% or lower if I was really an 80% free throw shooter. So according to this, the probability of me being an 80% free throw shooter and going outside and only making 64% of my 50 free throws is 3 out of 400, or 0.0075. Now that probability is very small. So what we can do with that probability is we can say, yo, Mr. Walsh, I have strong evidence that you are not an actual 80% free throw shooter. In fact, I have strong evidence that you are less than an 80% free throw shooter. Because if you were an 80% free throw shooter and you were to shoot 50 free throws and only make 64% of them, the probability of that happening is 3 out of 400. It's very rare. Okay, so there's two things that could be possible in this scenario. Option number one, the null hypothesis is correct. I'm actually an 80% free throw shooter, and just by chance, you saw this very rare occurrence that I shoot and make 64% of my 50 free throws. Because I didn't say it was impossible to happen. It's just very unlikely. If we were to do that 400 times, you would see it 3 times. So the probability of you seeing it at that moment is very small. The other thing that's probably that could be happening is the alternative hypothesis is correct. And that alternative hypothesis was that the population proportion was less than 0.8, meaning that I actually shoot and make less than 80% of my free throws. Now, the alternative hypothesis being correct is more logical in this scenario because of my probability of the event occurring being so small. So the basic idea is if the outcome that would rarely happen, an outcome that would rarely happen if the null hypothesis were true is good evidence that the null hypothesis is not true. So, for example, the outcome that we got would very rarely happen if the null hypothesis was true. Therefore, the null hypothesis is probably not true. Okay. When we're doing a significance test, we're going to get this thing called a p-value. Okay. The p-value is the probability that measures the strength of the evidence against a null hypothesis. What does that mean? Well, a p-value is the probability of the event the probability of the outcome occurring given that the null hypothesis is true. So again, a p-value is the probability that the outcome occurs given that the null hypothesis is true. In our context, the probability of me shooting 50 free throws and making 32 or less, because that was the outcome, given that I'm actually an 80% free throw shooter, that probability is the p-value. So in our simulation, that p-value was 3 out of 400 or 0.0075. Small p-values give us evidence against the null hypothesis because they say that the observed result is so unlikely to occur if the null hypothesis is true. So therefore, the null hypothesis probably isn't true. A large p-value fails to give convincing evidence against the null hypothesis because they say that the observed result is likely to occur by chance if the null hypothesis is true. Notice that even large p-values don't tell you that the null hypothesis is true. They just say that the null hypothesis is not false. Okay, so there's going to be a difference between what we call rejecting and failing to reject. Okay. The final step in a significance test is concluding it. Okay, you're either going to reject the null hypothesis or we're going to fail to reject a null hypothesis. Okay, we're never, ever, ever going to accept a null hypothesis. We either reject it or fail to reject it. For example, in our context of the problem, we have a null hypothesis that p equals 0.8. The alternative is that p is less than 0.8 because you guys think I'm no good at basketball. We then did a simulation and we found a p-value, which is the probability that I shoot and make only 32 out of 50 free throws, given that my free throw percentage is really 80%. That p-value was 0.0075. So you are going to reject my null hypothesis because it's very small p-value. Small p-values reject null hypotheses because you think the null hypothesis is wrong. Now, let's just say we got a p-value of like 0.4. If I was to go out and instead of making only 64% of my free throws, I made, say, 75% of my free throws. Now, 75% isn't that much different than 80%, which is my claim. So at that moment, you're not going to accept my claim. You're just going to fail to reject it. You're going to say, you know what, Mr. Walsh? I don't have enough evidence to say that you're wrong, but I'm not going to accept the fact that you're right. Okay? This happens a lot when in the real world when we're doing a significance test and they make a claim and they can't deny the claim. They can't reject the claim. So they failed to reject it. And what often happens is when you fail to reject, you are going to have to gather more data to make more conclusions. Okay. So again, rejecting and failing to reject. Those are our only two options when we are making a conclusion. A small p-value rejects the null hypothesis, gives us convincing evidence for the alternative. A large p-value fails to reject the null hypothesis, not giving us evidence for the alternative. We're never going to accept the null hypothesis. You're never going to say the null hypothesis is right. You're either going to reject it or fail to reject it. Now, I keep saying small p-value and large p-value. So how small is small? Well, there's a thing that we got to compare it to. We got to choose a value called alpha. And this is the significance level. And alpha is what we're going to compare our p-value with. So how small is a small p-value? Well, we're going to choose an alpha level called the significance level. And this will determine what size of a p-value we need to reject versus failing to reject. Okay? If the p-value is smaller than alpha, then the data is statistically significant. If the p-value is smaller than alpha, we're going to reject the null hypothesis. If the p-value is larger than alpha, we're going to fail to reject the null hypothesis. So we're always going to compare a p-value to alpha. You choose an alpha level before you do the test. Usually your alpha level is like 5% or 0.05. Sometimes it's 1%, 0.01. Depending on the context of what you're dealing with, it could even be smaller than that in real life, 0.005, which is 0.5%. But you're always going to compare this p-value to a significance level called alpha. Okay, so let's go to our claim here. Let's see if we can outline a significance test. I am shooting free throws and we made a claim. And our claim was that H naught was that P is equal to 0.8. And my alternative, which is what you guys said, because you think that I'm no good at basketball, P is less than 0.8. Okay. We chose a one-sided test because you guys don't care if I'm any better than at basketball. You just want to know, am I worse? Choose an alpha. All right, let's choose an alpha. Let's just say the alpha is equal to 0.05, 5%. Okay, meaning that any outcome probability that's below 5%, we're going to reject the null hypothesis. Any outcome probability that's above 5%, we're going to fail to reject the null hypothesis. We're going to choose a sample. So our sample size was size 50, and we got a p-hat value of 32 over, this should be a 50, not a 60, sorry. Our p-hat was 32 over 50, also known as 0.64. Okay. Now, we reject or fail to reject. When we did our p-value in our little example, we used a simulation to get a sampling distribution. But we don't need a simulation, right? We know how sampling distributions work, right? We are essentially, here is my distribution. We're going to assume my claim is true. So here's the center of my distribution, 0.8. And here is 0.64. Okay, because that's my p-hat. Here's P. And we want to know what is the probability that p-hat is less than 0.64. Now, in our simulation, we got 3 out of 400 because we took 400 samples of size 50. But now we're doing a real sampling distribution, so we're taking an infinite amount of samples of size 50. Our task is to find this area here. Now that area right there is our p-value. That's the probability of getting a p-hat of 0.64 or less, given that 0.8 is true. How do we find that? We can use a normal distribution. We can say that norm CDF, lower bound we'll call 0, upper bound is 0.64, mean is 0.8, standard deviation is going to be the square root of 0.8 times 0.2 over n, which is 50. Okay. This is the real p-value. The p-value that we found in our simulation will be close to this, but it won't be the actual p-value. So let's go ahead and use normal CDF and see if we can come up with a true p-value here. Let's go ahead and use normal CDF, lower bound 0, upper bound 0.64, mean 0.8, standard deviation would be the square root of 0.8 times 0.2 divided by 50. Now you might be asking, why am I using 0.8 here instead of 0.64? Because we're always assuming that the parameter p is true. We assume it's true until we can prove that it's not true. So my standard deviation, my sampling distribution, is based off assuming that the parameter is true. That's why I'm using 0.8. And I get a p-value of 0.0023. So this is our p-value, 0.0023 equals p-value. And that is the probability of me shooting 50 free throws and making 32 or less, given that I'm actually an 80% free throw shooter. Okay, a little bit different than the simulation p-value that we got. Our task is to compare, is to either reject or fail to reject. In order to do that, we have to compare this to our alpha level of 0.05. So since 0.0023 is less than 0.05, we are going to reject the null hypothesis. We're going to reject H naught. We're going to say, I have convincing evidence that Mr. Walsh shoots and makes less than 80% of his free throws. I'm not saying, see how I'm saying I have convincing evidence? I'm not saying it for certain. Nothing's set in stone here because this probability isn't zero. There is a small chance that you saw a miracle happen today, but it's highly unlikely. That's why I say I have convincing evidence. I'm not saying that it's 100% true. Okay. What could go wrong? Well, there's two types of errors when we're drawing conclusions. It's type 1 error and type 2 error. Okay. Type 1 error is if we were to reject the null hypothesis when the null hypothesis is true. This means this could happen in the example I gave today. Type 1 error is if you were to say, Mr. Walsh, I reject your hypotheses, but actually my null hypothesis is true and you just saw a super rare occurrence. That's type 1 error. It could happen, right? Type 1 error. Type 2 error is if you fail to reject the null hypothesis when the alternative is actually true. So for example, if I claim that I can make 80% of my free throws and I go ahead and I shoot 50 free throws and you guys look at the data and you say, okay, Mr. Walsh, I failed to reject your claim. Maybe you are actually an 80% free throw shooter. And I'm like, whoo, thank God, because I'm not actually an 80% free throw shooter. Okay, I fooled you guys. Okay, that's type 2 error. It's when you fail to reject, but you should reject. And here is a little chart that you will see. Okay, type 1 and type 2 error. The probability of these occurring can be calculated. The probability of type 1 error occurring is always your alpha level. So if alpha is 0.05, then the probability of a type 1 error is 5%. If alpha level is 0.01, then the probability of type 1 error is 1%. You might be asking me, well, then why don't we just choose a really small alpha? So that way we eliminate type 1 error. Yes, however, the smaller you make alpha, that means you're going to increase the probability of type 2 error because they work inversely. Okay, so in the context of your study, you'll have to analyze which one is worse, making a type 1 error versus making a type 2 error, and that will help dictate your alpha level. Okay, so you gotta consider the consequences of making a type 1 error and a type 2 error before you choose a significance level. And it really depends on what you're looking at and what field of study you are in real life. And that is the end of today's lesson. Okay, I hope you enjoyed it. I'm going to go outside and practice my free throws.